G'day chemistry students. In this video we're looking at dot points again, 3.3.1, 2 and 3. In this video again we're looking at reaction rate, but we're looking at how catalysts influence it. Let's get into it. So what I want to talk about first is the idea again of activation energy. Now, activation energy that we can see here on the right is the amount of energy required for a collision to occur that will lead to a successful reaction where reactants turn into products. And so what we can see on this graph is two versions of the same reactions. We start with the same reagent and we end with the same products. But what we're comparing is an uncatalyzed versus a catalyzed reaction. Now, to distinguish the difference, catalysts help reactions proceed in ways which require less energy. So what that means is that for a catalyzed reaction, reagents will still turn into products, but it will do so in a way in which the catalyst isn't actually reacting. It's not turning into a product that wasn't a reagent to begin with, but it is involved in the reaction in some way, shape, or form, which means that the process has a lower activation energy. Now, what that means is there are going to be more chemical processes which lead to successful collisions. Those successful collisions then mean that the reaction can occur at a greater rate. Now, I've got an animation over here showing the action of a catalyst. It's a reaction involving nitrogen and hydrogen. So nitrogen is in blue N2 and hydrogen is in white H2. So if you have two nitrogen atoms or one N2 particle reacting with those 6 hydrogen atoms there or 3 H2 molecules, you can end up forming 2 lots of NH3 ammonia. Now, this is known as a Haber process, a really important industrial process, in particular used to produce fertilizers amongst other things. And this reaction actually has quite a large energy requirement. And so industrially is quite a tedious and expensive process potentially to be able to yield lots of ammonia gas. And that's not necessarily because of the energy requirements to form NH3, but rather to break down the nitrogen and the hydrogen gas present so that they can then reform into NH3 ammonia. And so that is then the role of this catalyst. Now, the catalyst could be a number of things, usually some sort of metal oxide. It's a surface on which the diatomic nitrogen and hydrogen can attach, and the metal oxide, whatever it is, in some way, shape, or form, helps to break down those bonds, which then enable them to reform into ammonia. Now, without it, what that would mean is we'd be following a process that runs the blue line. There would be a much larger energy requirement that would be needed to enable the process to proceed forward. Note that this reaction is operating with a catalyst and is still needing temperatures that exceed 400 degrees Celsius. Now, if the catalyst didn't exist, that energy requirement would be even greater, meaning that potentially the reaction could be a lot less profitable or so inefficient that it wouldn't even be a viable process. So a lot of the time when we talk about catalysts usually enable a reaction to happen under a certain set of conditions. A concept that we're going to be expanding on a lot more in modules 4 and 5. But notably as well, if you have more particles which are able to exceed a set activation energy which has been lowered by a catalyst, that can also just mean that the reaction rate will increase as well, and thus can be a factor which can influence reaction rate, something that we'll be looking at in class next lesson. And that brings us to the end of Module 3. Congratulations. There's only going to be one more module for Year 11. That's Module 4, all about thermodynamics and the energy of reactions, something that we've been already building towards over the last couple of weeks. Hope you enjoyed the break, and I'll see you in the next module.